very entertaining watching me do this. Just relax, okay? Hello? Okay. 3 minutes in. Everything seems to be going fine. Not sure if you can hear me, but I hope so. I hope so. Yeah. 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 Okay. Oh, wow. Let me blow out my speakers, huh? All right. So, welcome back. We're here to learn some statistics. Last time, we were still working our way through this MIT course. So today what I want to do is keep on crushing it. Hold on. Hold the phone. Hold on. Relax, people. Relax. I think this is number 7. 7. MIT Intro to Probability and Statistics. What's today? Today is the 26th. No? Yes. 7. 26. 23. Alright. Save. Saved. Did that save in the right spot? Yes. Saving. Cool. Pop that puppy back open. And we are ready to get into it. I'm ready to get into it. Such excitement. But really though, this is cool stuff. We are learning about knowledge. We're learning about truth. We're learning about how it is a way of knowing, okay? We're learning how to learn. We're learning about statistics so we can learn through statistics. I finally got it out of my flapping gums. Flapping gums? Ugh. Okay. Where are we? We are going back to De Morgan's laws. Last time, we covered a bit about who De Morgan even was. Some old guy. He was some old guy. And now he's some dead guy. But his laws remain. His laws remain, and we're gonna learn about them. And then we're gonna go to YouTube. And we're gonna watch some Zed statistics, and he's gonna explain to us how hypothesis testing works. And then maybe if I'm not too bored, maybe if I'm still feeling excited, riveted, intrigued, perplexed, and therefore incentivized to go forward and continue learning, maybe then we'll do a deep dive through Wikipedia about statistics as a field. This is a learning adventure. You're there, I'm here, and we're in this together. You and me from the start. Thank you for joining me. Let's get into it. All right, so here we have De Morgan's Laws. We're opening that puppy up. We are waiting for our German sounding instructor who may or may not be German. This does not look like a German name. Sitziklis. Sitziklis. He probably said it in the first thingy, the first video. But today, we're not worried about pronouncing his name. We're gonna watch the content.
We will now discuss De Morgan's laws, that are some very useful relations between sets and their complements.
Okay. Right off the bat, what did we learn? We learned De Morgan's laws are about sets and their complements. So right now we're invoking set theory, right? Set theory. Awesome. And then where do we go from there? Well, we learn about sets and their complements. Sets and a complement. So like how this relates to probability is that you have the what's it called? The little population you have. You have the total set, which is the omega, right? The omega, that's what it looks like, right? You have the omega, which is the total population, and then you have the subsets of the population. And so that's all just thinking in terms of sets, and the complement of a set is those parts of the set that aren't the set, you know? Like the subsets that aren't the set. You're so smart.
One of De Morgan's laws takes this form. If we take the intersection of two sets and then
the intersection of two sets, that's different from the union of two sets. It's the intersection. If you have a Venn diagram, the intersection is the middle part. It's that simple. So this is a very complicated way of saying the middle part of basically a Venn diagram.
take the complement of this intersection, what we obtain is the union of the complements of the two sets. Pictorially, here is the situation.
Yes,
we have our universal set.
I know we covered this last time, but we're doing it again. We gotta review. And you know what? Before we do any of this, let's really ingrain those axioms, huh? Those axioms, because I always forget the last one. I said this last time too. So, you know what? We're gonna do that right now.
We have so far discussed the first step.
Okay, so yeah,
we've got be expected to have positive probabilities. So
so we've got the axiom of non-negativity. We've got the axiom of normalization. That is any probability can be described in terms of being less than 1, less than or equal to 1, because in any situation there's always the at most a 100% probability that that event is going to take. That makes sense. I don't know if that's quite right, but we're not doing a deep dive right now. So we've got non-negativity, normalization.
It should always be equal. We have in different language, we have absolute certainty that event omega is going to occur.
Yes.
And we capture this certainty by saying that the probability of event omega is equal to 1. These two axioms are pretty simple and very intuitive. The more interesting axiom is the next one that says something a little more complicated. Before we discuss that particular axiom, a quick reminder about set theoretic notation. If we have two sets, let's say a set A and another set B, we use the notation, we use this particular notation, which we read as A intersection B, to refer to the collection of elements that belong to both A and B. So in this picture, the intersection of A and B is this shaded set.
Yeah.
we use this notation, which we read as A union B, to refer to the set of elements that belong to A, or to B, or to both. So in terms of this picture, the union of the two sets would be this blue set.
Cool.
After this reminder about set theoretic notation, now
Got
let
it.
us look at the form of the third axiom. What does it say? If we have two sets, two events, two subsets of the sample space, which are disjoint. So here's our sample space, and here are the two sets that are disjoint.
Uh-huh.
In mathematical terms, two sets being disjoint means that their intersection has no elements, so
Yeah,
their
that makes sense.
intersection is the empty set, and
Got
we
it.
use this symbol here to denote the empty set.
Cool.
So if the intersection of two sets is empty, then the probability that the outcome of the experiment falls in the union of A and B, that is, the probability that the outcome is here or there, is equal to the sum of the probabilities of these two sets.
Okay, that makes sense.
This is called the additivity axiom. So it's
Okay, so this is the third axiom. The third axiom basically means if you got a square, you got two spaces in that square, probabilistic spaces, right? There's no intersection. So what that basically means is you can add them up to equal the total area. Adding them up would equal the total area that a probability would occur. You can just say A plus B, right? But if they're intersected, and I think that he gets into this, if they have any intersection, you have to subtract from one of them that area. But you wouldn't have subtracted from both of them because you've already accounted for it. I think that's where he goes.
says that
right? Or maybe
we
it's
can
just
add
finite
probabilities
additivity.
of different sets when those two sets are disjoint.
Yeah.
In some sense, we can think of probability as being 1 pound of some substance which is spread over our sample space, and the probability of A is how much of that substance is sitting on top of a set A. So
Yeah.
what this axiom is saying is that the total amount of that substance sitting on top of A and B is how much is sitting on top of A plus how much is sitting on top of B. And that is the case whenever the sets A and B are disjoint from each other.
Got it.
The additivity axiom needs to be refined a bit. We will talk about that a little later. Other than this refinement, these three axioms are the only requirements in order to have a legit.
Okay, so we went over all of this, but we're trying to retain it, right? So this is finite additivity, which basically means you add the A and the B together. This is the third axiom. So non-negativity, normalization, and finite additivity. Like adding, like you're adding them up. Additivity. It's there in the name. Okay? All right, good. You got all that? So I'm just gonna, as a refresher, no, stop it. Refresher, bop, bop, bop. The three axioms of probability are 1. Non-negativity. 2. You like that? 2. Normalization. And 3. Finite additivity. Hope I spelled everything right. And we are going in to De Morgan's laws again, right? And De Morgan's laws are ways of thinking about sets, and we're gonna just
The
punch
intersection.
ahead.
What we obtain is the union of the complements of the two sets. Pictorially, here is the situation. We have our universal set.
Cool.
Inside that set, we have a set S, which is this one.
Right.
And we have another set T, which is this one.
Okay.
Let us look at this side. The
Right.
complement of S is this part of the diagram.
That
The
makes
complement
sense.
of T is this part of the diagram.
Sure.
What is left? What is left is just this region here, which is
Sure.
the intersection of S with T. So anything that does not belong here belongs to the intersection, and this means that the complement of the intersection is everything out there, which is this set. If you are not convinced by this pictorial proof, let us go through an argument that is a little more formal.
Okay. So what this is saying is that the complement of the intersection of S and T is equal to the complement of S, the union between the complement of S and the complement of T. So if you have an intersection, everything that isn't S and everything that isn't T together are going to equal everything that is the complement of the intersection of S and T. Okay, I think I got it.
What does it take for an element to belong to the first set?
We're definitely going to review that again next time.
In order to belong to that set, X belongs to the complement of S intersection T. This is the same as saying that X does not belong to the intersection with S with T. What does that mean? Since it is not in the intersection, this is the same as saying that X does not belong to S or X does not belong to T. But this is the same as saying that X belongs to the complement of S or X belongs to the complement of T. And this is equivalent to saying that X belongs to the union of the complement of S with the complement of T.
I
So
see.
this establishes this first De Morgan's law. There's another.
Okay, so this is the first of De Morgan's laws. De Morgan's laws is about, what did we say? We said are about sets and their complements, right? So we're talking about sets and we're talking about complements. This is related to probability because probability has to do with basically you have spaces, you have populations which can be represented in terms of spaces, and you have subpopulations of which you derive your conclusions from using the probability tools that are available to you. Okay, so here we have Mr. De Morgan's laws. He's talking about sets and complements. And we established in the beginning here, Mr. Tsitsiklis, John Tsitsiklis, this guy, showed us a pictorial proof. So here we can see that the intersection, and remember an intersection is the Venn diagram, the intersection of the Venn diagram, right? The places where they overlap. And down here we can see, we learned last time that this little e means belong, right? So we have X belongs to the complement of the intersection of S and T. So X, there exists some X that belongs to the intersection, the complement of the intersection of S complement T. It exists somewhere on here. If and only if X does not belong to the intersection of S and T. So it can only exist in the complement if and only if it doesn't exist in the intersection itself. If it's either there or it's not there. It's that simple. and that's another way, if and only if x does not equal s, does not belong to the set of s, or x does not belong to the set of t, has to be either one of those if and only if x belongs to the complement of s, or x belongs to the complement of t if and only if x belongs to the complement of s and the complement of t. So what's throwing me off? If I'm just thinking out my thought process right here, we've got Mr. X here does not belong to S or does not belong to T. What's throwing me off is if it didn't belong to S, couldn't it therefore belong to T under this notation? But it can't belong to T. It has to be neither belonging to S or belonging to T. At least that's how I've been understanding it. So I'm a little thrown off. I'm not grokking it as well as I can. But we will not stand for standing in place. We must challenge forth. Hopefully my brain will stretch enough to really intuitively get this. But right now I'm just having trouble getting it through my thick skull. So we will... we're going to formulate a question. So if it is the case... I'm going to think I'm so stupid later, but... We wanna be supportive of our learning challenges, okay? We're gonna accept that we don't fully get it. We get part of it. We're not completely misunderstanding here, but we've got some room for growth. So if it is the case that x belongs, we're gonna write it out because I can't do the little symbol for x does, there's a way to do it, but I forget, does not belong to S, or x does not belong to T, Can you see the smoke? Can you see the smoke? This shouldn't be this hard. Normally what I would do is pretend that I understood and say, oh yeah, I totally get this, but I'm actually trying to understand it, so that's the challenge.
Which is obtained from this one by a syntactic substitution. We're going to play the following trick. Wherever we see an S, we're going to replace it by S complement, and wherever we see an S complement, we will replace it with an S. And similarly, whenever we see a T, we'll replace it by T complement, and when we see a T complement, we will replace it by T. So doing this syntactic substitution, what we obtain is S complement intersection with T complement, everything gets complemented, is the same as S union T. Now let us take complements of both sides. The complement of a complement is the set itself. So
I remember
we
this.
obtain this. And now we take the complement of the other side, which is this one. And this is the second De Morgan's law. It tells us that the complement of a union is the same as the intersection of the complements. We derived it from the first De Morgan's law by a syntactic substitution. If you're not convinced, it would be useful for you to go through an argument of this kind to show that something is an element of this set if and only if it is an element of that set as well. Finally, it turns out that De Morgan's laws are valid when we take unions or intersections of more than two sets. There is a more general form, and the general form is as follows. In analogy with this one, if we have a collection of sets, Sn, perhaps an infinite collection, we take the intersection of those sets and then the complement, What that is the union of the complements. So this is analogous to this law. And this law extends to this one. If we have the union of certain sets, and we take the complement of the union, what we obtain is the intersection of the complements.
I feel like this is simultaneously easy and difficult at the same time. Like, I get it, but also I don't. Love that for me. Alright, what about this one? How long is this one? 6 minutes. 6 minutes? Sequences and their limits. Well, okay, here's what we're gonna do. Buddy. Pal. Here's what we're gonna do. We are gonna take a moment to check out hypothesis testing. Super exciting, I know. But if you are joining me, I appreciate it. I thank you very much for joining me. I really value your joining of me at this moment. And if you find any of this valuable, maybe you're preparing for, you're at university. Maybe you're a data analyst trying to grok this stuff a little better. Any of those things. If you're joining me on this journey, I appreciate your time. And if you find any of this valuable, please consider contributing to me at patreon.com/mindofmeaning. We here at this channel, we're a channel pursuing truth. We see statistics and probability as one technique among many for understanding true things. It is the thing through which we understand certain types of true things. It is not a panacea. It is not everything. It is merely what I'm starting with on this channel. And we're going to enjoy the process. We're going to learn some statistics. We're going to learn some probability. And we're going to get paid while doing it. That's right. So consider supporting me. Patreon.com/mindofmeaning. And with that, we're moving on to our next segment. Our next segment is going to be watching Mr. Zed Statistics here go over hypothesis testing. This is a whole hour and 8 minutes long, which means, given how frequently I stop these things, it's going to be much longer. But we're going to try and enjoy the process, really understand the process, and maybe in the meantime, we're going to jump back over to Mr. MIT with Mr. Tick and try to understand what he's talking about. And we're gonna develop such a firm foundation. It's gonna be so firm and well grounded that we're gonna basically be geniuses. And that's a fact. Okay. Now, back into it.
And welcome to the third video on statistical inference, this one being on hypothesis testing. My name's Justin Zeltzer, and I'll put all the videos in the series up on zstatistics.com, or if you're watching via university, you'll be able to see them in each of the module pages. So this will be module 3. Now this is quite an extensive look at hypothesis testing, so if you're new to it, see if you can get through the video, because it really is quite a complete picture of hypothesis testing. And I'm going to start with a bit of a look into the intuition behind hypothesis testing. It won't involve any numbers, but I think it's quite a good way to start to get us get our minds in the right frame for it. We're then going to look at an example, and that's going to lead us through the rest of the video. So we'll use that example. We'll use that example in looking at all the other subtopics. And after we get familiar with this example, we're going to look at these first 3 subtopics, which are all somewhat related. The first one is about the null hypothesis. We'll be defining what that is, looking at the alternate hypothesis as well. We'll be dealing with this concept of level of significance, which is a very important concept.
This seems
we'll then
very
look
familiar.
at this idea of a test statistic. So in any given hypothesis test, you generate one of these. And in doing so, you can also generate an accompanying p-value. the
He
much
has a very
maligned
soothing voice.
p-value in statistical circles, at least. We'll be looking at all three of these concepts, which, as I said, are all related. And what I mean by that is that they have the same perspective, which is the null hypothesis. We'll see what that means when we get there, but they all essentially assume the null hypothesis is true. Anyway, after that, we'll go on to discussing what a confidence interval is all about.
Confidence.
We've kind of loosely touched on this in previous videos in the series, but the reason why I'm bringing it up again here is that it's kind of like an equal and opposite measure of the p-value. They actually work in tandem, but the difference being confidence intervals have the perspective of the sample, whereas your p-value has the perspective of your null hypothesis. So look, if these terms don't mean anything to you, just hold on 2 seconds and we'll get into it in earnest.
Ernest.
If you've been to your lectures and you've sort of heard these terms thrown around, I'm just
Stay
giving
in
you a bit
school,
of a picture
kids.
as to where we're going to be dealing with them. We're then going to look at significant treatment difference, power and sample size as well. And this is actually my favorite bit, so if you can stick around to the power and sample size section, I think, if I can say so, I do a pretty good job of trying to get an intuitive look at power and sample size as well.
Hello, trouble.
So with all that done, we'll finally have a look at an example here, a different one, and it'll give you a chance to put what you have learnt into practice.
That's
There's
right.
quite a lot of algebra here as well.
Algebra.
So there's a lot to get through, but it should be a fun little journey, and hopefully by the end, you're going to be tip-top around your hypothesis tests.
Cheerio.
So let us begin with the intuition behind hypothesis testing.
I'm ready. I'm ready.
So say that you think $1 coins are tail biased.
They
What
are.
I mean by that is that maybe they flip more tails than they do heads for whatever reason. Maybe there's subtly more coin on the head side of the coin, so it weighs it down or something like that. I don't know. It's a silly example, but at least it gives us something we can visualize. The question is how you would test this hypothesis scientifically.
With a hypothesis.
Now, you might tell me that firstly, you got to flip a bunch of coins, obviously. You got to take
Yeah.
some kind of sample or
Duh.
do an experiment, and that's true.
True.
You then have to get out a pen and paper and note the proportion of tails you have in your sample. But then what? What happens then? How do you know whether, yes, this coin is now biased, or no, this coin is not biased? Well, that's where hypothesis testing is going to come in and help you out.
I'm ready.
It's going to help you solve this riddle of yours that you've constructed for yourself. And I've put together a visualization to help us out here. This is
The
the number of
normal
tails
curve.
from 100 tosses of a fair coin. Now, the important part of this sentence is the word fair there. So if the coin was fair, as in not biased, you might expect this being the probability distribution of possible outcomes from that 100 tosses of the coin. It's not as if you have to get 50 tails from your 100 tosses of the coin, right?
Yeah, you do.
You might get
have
51 or 52, or it's even possible to get, say, 60 or 61 tails.
Talking nonsense
out of
then.
100.
That's ridiculous.
And it's still come from a fair coin. It just so happened you had a very random sample, very extreme sample. Now, before we interrogate this further, I'm going to change this from the number of tails from 100 tosses to the proportion of tails from 100 tosses of a fair coin. Nothing else changes. 50 now becomes 0.5. This just allows us to generalize beyond this particular number of tosses of the coin.
But Zed, how
So
does
yes,
it do
looking
that?
at this distribution, you might notice that it's centered around 0.5.
Yeah, I do
And that
notice
indeed
that.
is what we might expect to get from our sample. That's our
That's what I would
expectation.
expect.
But say we had a sample that we got 52 tails in.
Doesn't make any sense.
Is that necessarily evidence of bias in this coin? Well,
For
no. It seems
sure.
quite reasonable that from a fair coin we could have just got 52 tails out of
Oh, I
100.
see your point.
But what then if we get a sample of 62 tails?
That doesn't make any
Does
sense.
that cast any doubt on the idea that the true proportion, that the true probability is 0.5?
I am filled
Well,
with
if you
doubt.
can see that this sample outcome casts more doubt on the coin's fairness than this sample outcome, you've effectively got the right mind state for hypothesis testing, and that's in fact all we're doing. We're assessing our sample for how extreme it is. That's all a hypothesis test is. It looks at a sample and asks, how extreme is that sample? And what'll happen is we'll create this barrier
all right. I remember watching something like this before from this guy before. I think it was a simplified version of this video, right? But if you've been paying any attention, class, you would notice, yes, if your sample is above a certain threshold, a hold of thresh, then it would make sense for your doubt to be greater. It's plausible, at least. So it seems. Or would it? Is there any situation in which it would make sense for this to occur in a fair coin? Well, maybe over the course of 100 tosses, you're just like really intuitively know how to flip a tail, right? But maybe over the course of like 1,000 tosses, maybe this goes down, you know. There's always like statistical anomalies in how we do things, right? In the activity. So say you have like 1,000 people flipping 100 coins, right? You have 1,000 people. Now you take all of those people and you put their results, the average of their results on a distribution. You may have people who get, 62 tailses, and they all had fair coins. So, it's in theory possible, but you would want to examine it, right? I think that's how this works. I'm trying. It's really hard to get the old thinker thinking and stuff. Okay, let's keep going.
Value, beyond which we're happy to say, yeah, it's now becoming too extreme for us to really maintain this coin's fairness. But if our sample lies on the left side of this, so say we got this 52 tails outcome, we might say, yeah, look, it's greater than 50, but it's not extreme enough. It's well within the realms of possibilities from a fair coin. That, my friends, is a hypothesis test, where your null hypothesis, your sort of starting value, might be that theta, the true...
Give me a second. Okay.
True proportion of coins is 0.5. That's that black line there. And we're going to see if we have enough evidence. We're going to see if our sample is extreme enough to suggest that the true proportion is greater than 0.5. In other words, this coin is biased. So we're going to use this sample of 100 coin tosses to make an inference about the true population probability, theta. Now, as I said, this value here might be our critical value. And beyond this point, we're going to start saying, yep, that is now too extreme for us to realistically hold on to this null hypothesis of theta being...
But Zed, how do we determine what our critical value is?
.5. And that's actually called the rejection region. That's the region in which we will be comfortable rejecting our null hypothesis. Now, if you're a bit of a smarty pants or you've paid attention in your lecture, you might realize that there's two possible ways of looking at our alternate hypothesis. You might note we have a one-tailed alternate hypothesis here. So we're only going to be rejecting this null hypothesis in one direction. So in other words, if our tails vastly exceeds our heads. But it's also possible to do a two-tailed test as well. And the difference might be, instead of having a strict one-sided inequality in the alternate hypothesis, this one, it actually goes both ways. So we'll have two different critical values. What this means is that if we have a sample that is extreme in either direction, we're happy to reject our null hypothesis. So it really depends on what kind of question you're asking. Are you asking specifically about the coin being tail biased, as in more tails than heads? Or are you asking whether the coin is just biased in general? And if it's the latter, we might have two rejection regions, one on the extreme positive side and one on the extreme negative side. But again, all we're doing is looking at the sample value and saying, how extreme is it? Is it too extreme for us to maintain this null hypothesis?
Is it? Is it that extreme?
Okay, so I feel like I've massaged your skulls into the right, so that they are now perfect absorbency for the actual nuts and bolts of all this. So let's have a look at the example I've provided here. And these two examples I give on this particular lecture here are both to do with the same surgical concern.
To operate,
which is to operate or not to operate. This first example deals with proximal humerus fractures in the elderly. That's something in the shoulder.
I, for one, find fractures in the elderly very humorous. Just kidding. Just kidding, okay? Chill, relax.
I'm told. Can you tell I'm a statistician and not someone medically trained? Nonetheless, we can do the stats on this. We have two particular treatment options here. We have an operative treatment, and we also have physio only. So for the operative patients, or the patients that were treated operatively, 62 had positive outcomes out of 100 after 6 months, whereas those that were given physio only had 48 out of 100 with an improved outcome after 6 months. So this is a very simplified example, obviously, with nice round numbers, so we don't have to get too numerically intense. The question is, can we conduct a full hypothesis test to answer the following questions? Is there evidence of a difference in outcomes between the two treatments? Is there evidence in a difference in outcomes? And B, say the Orthopedic Society requires an outcome improvement of at least 5% before updating treatment protocols. Should they recommend surgery for proximal humerus fractures? So here the idea is that it's not just good enough that operative treatment is slightly better than physio. They need it to be at least 5% better than physio.
At least
to start 5%. Recommending surgery. So let's maybe there's an additional there might be additional risks to the patient when they go under the knife. So those additional risks need to be offset by this additional buffer here. Anyway, feel free to actually, if you think you're confident you know how to do these sorts of questions, by all means, stop the video here and have a go and see if you can come up with an answer. But I will hint at this being a two-tailed test. So you can see we've asked, is there evidence of a difference in outcomes? So it doesn't matter which way it goes.
I'm here to learn, buddy, not to do work. Teach me.
Our hypothesis test here will be two-tailed. All right, let's tuck in. Let's talk about null hypothesis. So finally, we actually get to deal with some of the theory here. Let's call for to start with P1, the probability of a positive outcome for the operative group, and P0 is the probability of a positive outcome for the non-operative group, the physio-only group.
Okay, so null hypothesis, probability of positive outcomes for operative group, P0, probability of positive outcome for non-operative group. You know what I don't have? A better understanding of the null hypothesis. Now, we've covered this before, but you know, sometimes it takes a couple times for these things to sink into my brain. So, we're going on an adventure, team. If my computer ever speeds up. Null hypothesis. Null hypothesis. Okay. You know what? Professor Essa, you are gonna tell us about the null hypothesis. We're gonna get a little remembrance.
In this video, I'll be showing you what a null hypothesis is. I'll also be showing you a couple of examples of how to state the null hypothesis. A null hypothesis is basically an accepted fact. Not so long ago, the accepted fact was that the Earth was flat. Of course, we know it isn't flat now, but in order for people to accept the fact that the Earth is not flat, we had to have some scientists nullify or void the null hypothesis.
This is a controversial thing to show on the internet.
So scientists like Copernicus came in and said, no, the Earth is not flat. So that became an alternate hypothesis. So Copernicus set out to prove that the Earth is round by nullifying the null hypothesis. So the null hypothesis is an accepted fact. It's something you're going to set out to disprove. The null in the word null hypothesis means it's nullifiable. Nullify is just another way to say invalidate. A few more examples of a null hypothesis. The null hypothesis could be the Earth revolves around the Sun. The alternate hypothesis would be it doesn't. The current thinking about DNA, the null hypothesis, is that the DNA is in a double helix. The alternate hypothesis is it's not a double helix. Now both of those are examples of pretty much accepted facts now. We know the Earth revolves around the Sun, and we know that DNA is in a double helix.
Okay, before I can really get this, we're going on an extended journey here. Just a little rabbit hole. Where did the term null hypothesis come from? What I want to be able to do. Okay, cool. We're going on a Wikipedia journey. Okay? Join me. Story time. This article may be too technical for most readers to understand. That's not normally the one I'm used to seeing, but you know, that is something. In scientific research, the null hypothesis, often denoted H sub 0, is the claim that no relationship exists between two sets of data or variables. No relationship exists between two sets of data or variables being analyzed. The null hypothesis is that any experimentally observed difference is due to chance alone. Once again, the null hypothesis is that any experimentally observed difference is due to chance alone, and an underlying causative relationship does not exist. Hence the term null. In addition to the null hypothesis, an alternative hypothesis is also developed, which claims that a relationship does exist between two variables. Okay, so they're basically saying it's either chance or it's not chance, or it's just chance. Okay. The null hypothesis and the alternative hypothesis are types of conjectures used in statistical tests, which are formal methods of reaching conclusions or making decisions on the basis of data. So every time you see data-based decision making, we are saying that we have a null hypothesis, and an alternative hypothesis is one way of making those conclusions and decisions. The hypotheses are conjectures about a statistical model of the population, which are based on a sample of the population. The tests are core elements of statistical inference. heavily used in the interpretation of scientific experimental data to separate scientific claims from statistical noise. Scientific claims, statistical noise. Heavily used interpretation of scientific experimental data. What's noise? What's claim? The statement being tested in a claim of statistical significance is called the null hypothesis. The test of significance is designed to assess the strength of the evidence against the null hypothesis. Usually the null hypothesis is a statement of no effect or no difference. It is often symbolized as H sub 0. The statement that is being tested against the null hypothesis is the alternative hypothesis. Man, feels like I'm reading in circles here, doesn't it? Symbols include H1, HA. Statistical significance test. Very roughly, the procedure for deciding goes like this. Take a random sample from the population. If the sample data are consistent with the null hypothesis, then do not reject the null hypothesis. If the sample data are inconsistent with the null hypothesis, then reject the null hypothesis and conclude that the alternative hypothesis is true. The following adds context and nuance to the basic definition. Given the test scores of two random samples, one of men and one of women, does one group differ from the other? A possible null hypothesis is that the mean male score is the same as the mean female score, or H sub 0, aka the null hypothesis, mu1 equals mu2, where H sub 0 equals the null hypothesis, mu sub 1, the mean of population 1, and mu sub 2, the means of population 2. A stronger null hypothesis is that the two samples are drawn from the same population such that the variances in the shape of the distribution. So, it doesn't really tell me the history. Principle, goals of null hypothesis. This is actually, we might come back and read some more of this at some point. Because we are going in depth, deeply, profoundly, and thoroughly into statistics and probability. We are trying to find truth through some means, not just statistic and probability, but by many different means. But we are starting here with statistics and probability. And if you find this content in any way entertaining whatsoever, even a smidge, which is a technical term, then consider supporting me over at patreon.com/mindofmeaning. Once again, that's patreon.com/mindofmeaning. That is my plug. Consider it. We're going back to Mr. Zed. He's going to tell us about the null hypothesis and give us some more details.
So our null hypothesis here is theta, which is the population parameter, or the difference between these two probabilities. We're going to set that equal to 0 in our null hypothesis. And our alternate hypothesis is that theta is not equal to 0. Now, in general, the way of thinking about a hypothesis test, or at least the attitude towards hypothesis tests from statisticians, is that we're always very pessimistic. So for example, say we're trying to show that there's a difference between these two groups. The first thing we do is we assume that there's no difference. So we assume that there's no difference and see if there's enough evidence to infer that there is a difference. We don't simply assume the thing is true that we're trying to show first and then try to disprove it. No. We're pessimistic. We always assume the reverse is true. So if we're trying to seek evidence for a difference, we'll first assume that there's no difference. And then in our alternate hypothesis, we'll have finally that there is a difference between these two groups. So another way of saying that is that whatever you're seeking evidence for, this is a really good line, whatever you're seeking evidence for goes in your alternate hypothesis. We are seeking evidence to show that there's a difference between the two groups. So that goes in our alternate hypothesis. And I can almost see the question now getting typed in the comment section, which is, can you seek evidence to show that the difference is zero? Can you seek evidence for sameness? My answer is, well, no, not really. Certainly not in very simple forms of statistics. So our null hypothesis will always be some kind of equality, and our alternate hypothesis is that inequality, seeking that difference. Now the question is, if the null hypothesis is true, how will the sampling statistic... Now for the moment, let's just say the sampling statistic is sort of theta with a hat on it, what we can get from our sample, which will be our samples P1 minus our samples P0. Now, if the null hypothesis is true, how will it be distributed? Well, much like our slide on the intuition behind hypothesis testing, it'll be distributed like a nice bell-shaped curve. So, again, the important part of this is that the null hypothesis here is assumed to be true. So if indeed there is no difference in the population between the two groups, our sample should expect no difference between the two sample values. And when I say expect, I mean that that's the middle of the distribution.
The middle.
Due to random variation, of course, there will be some kind of probability distribution around that, some kind of variance around this sample value of 0. But what variance?
What variance?
How can you
indeed?
describe this distribution? Well, the expected value of this distribution, as I just said, is 0. It's the middle of this plot, which
The
makes
middle.
sense because if the null hypothesis is true, if you sampled 100 patients that had the operative treatment and 100 patients that had physio only, you would expect them to have the same proportion of successful outcomes. That should be the middle of the distribution. But what is the variance of this distribution? Well, you'll note that we actually have two random variables here, P1 and P0. And this just involves a little bit of your recollection of linear algebra. The variance of two...
He thinks I took linear algebra. Actually, the truth is, there was a time when I was going through the Khan Academy linear algebra project. A long time ago. I played with it a bit, but I didn't really fully sink in. I remember matrices. I remember little X's and zeros and stuff. A little bit about that. I mean, it wasn't as hard as it could have been, but yeah, certainly not anything I remember to any great degree. But you know, thank you for thinking so highly of me.
uncorrelated random variables is just the variance of one plus the variance of the other. So the variance of a proportion is in fact that proportion times 1 minus the proportion divided by the number of observations. And the same will be true for the physio only group. Now if you recall, when we were looking at the contents of the whole video, I noted that this particular subtopic among 3 subtopics takes the perspective of the null hypothesis. We're assuming the null hypothesis is true, so that means that P1 and P0 are actually going to be the same. So what we can do here is that this distribution here assumes the null hypothesis is true, so that I can change this P1 and P0 into just P, which is this sort of grouped mean or grouped proportion. So they're actually the same here, and so we can simplify this a little bit to be P times 1 minus P times 1 on N1 plus 1 on N0. So theta hat, here we go, is distributed normally with a mean of 0 and a variance given by this. Now again, I see a question. Someone I'm sure is going to be asking me, why on earth is this distributed normally? We have a difference between 2 proportions. These are essentially binomial distributions. Why is this normal? And this is the lovely thing about statistics. As soon as you sample enough, as soon as your sample size is big enough, everything just becomes normal. I feel like every statistician should have a CLT tattoo on them somewhere. Without it, we would be much worse off. CLT standing for the central limit theorem, which allows us to put this big N here and say that in large samples, sampling statistics tend to become normally distributed. All right, so let's go in a little bit further. What's going to happen here is that we're going to construct, well, there'll be two separate rejection regions, each of which will have, well, there'll be two separate rejection regions, which in combination will sum up to 0.05. Now, why does it sum up to 0.05? Well, that's just our choice. We're going to label this thing called alpha as 0.05. And all that means is that this is the probability that we're willing to accept, we're willing to take on board in rejecting a null hypothesis that might be true. Right, let's just rewind that a little bit. If we get a sample in this yellow region here, we're going to be rejecting the null hypothesis. That's how we've constructed this hypothesis test. But realize that this distribution goes on for infinity. So this black line, the distribution, which is the probability density function, where the null hypothesis is true, it goes on for infinity. So it's still possible if our sample difference is 0.15.
Okay, we're taking a break from Mr. Zed. We're gonna definitely come back to master this material, but right now I want to pop back over to our friend, An Introduction to Probability. This gentleman right here. Okay? So we're gonna watch and learn
In this segment, we will discuss what a sequence is and what it means for a sequence to converge. So, a sequence is nothing but some collection of elements that are coming out of some set, and that collection of elements is indexed by the natural numbers. We often use the notation, and we say that we have a sequence AI, or sometimes we use the notation that we have a sequence of this kind to emphasize the fact that it's a sequence and not just a single number. And what we mean by this is that we have I, an index that runs over the natural numbers, which is the set of positive integers, and each AI is an element of some set. In many cases, the set is going to be just the real line, in which case we're dealing with a sequence of real numbers. But it is also possible that the set over which our sequence takes values is Euclidean space and dimensional space, in which case we're dealing with a sequence of vectors, but it also could be any other kind of set. Now, the definition that I gave you may still be a little vague. You may wonder how a mathematician would define formally a sequence. Formally, what a sequence is just a function.
I'm learning so much right now.
That
Can you
to
feel the
any
learning? Can you feel the brain
natural number
expansion?
associates an element of S. In particular, if we evaluate the function f at some argument I, this gives us the ith element of the sequence. So that's what the sequence is. Now, about sequences, we typically care whether a sequence converges to some number A, and we often use this notation, but to make it more precise, you also add this notation here, and we read this as saying that AI, as I converges to infinity, the sequence AI converges to a certain number A. A more formal mathematical notation would be that the limit as I goes to infinity of AI is equal to a certain number A. But what exactly does this mean? What does it mean for a sequence to converge? What is the formal definition? It is as follows. Let us plot the sequence as a function of I. So this is the I-axis, and here we plot entries of AI. For a sequence to converge to a certain number a, we need the following to happen. If we draw a small band around that number a, what we want is that the elements of the sequence as I increases eventually get inside this band and stay inside that band forever. Now let us turn this into a more precise statement. What we mean is the following. If I give you some positive number epsilon, and I'm going to use that positive number epsilon to define a band around the number a. So it's this band here. If I give you a positive number epsilon, therefore this way I have defined a certain band, there exists a time after which the entries will get inside the band. In this picture it would be this time. So there exists a time let's call that time I0. So I0 is here.
Okay.
Such that after that time
all the little pointies stay in the thing.
What we have is that the element of the sequence is within epsilon of a. So this is the formal definition of convergence of a sequence to a certain number a. The definition may look formidable and difficult to parse, but what it says in plain English is pretty simple. No matter what kind of band I take around my limit a, eventually the sequence will be inside this band and will stay inside there.
Okay.
Convergence of sequences has some very nice properties that you're probably familiar with. For example, if I tell you that a certain sequence converges to a number a and another sequence converges to a number b, then we will have that ai plus bi, which is a new sequence, the ith element of this sequence is this sum, will converge to a plus b. Or similarly, ai times bi, which is another sequence, converges to a times b. And if in addition g is a continuous function, then g of ai will converge to g of a. So for example, if the ai's converge to a, then the sequence ai squared is going to converge to a squared.
Did you get all that? I know I didn't. This is a lot. It's a lot to chew on. As someone who is never particularly good at math, but I mean, like, it's not completely incomprehensible. It's just definitely at my my stretch goals, you know, my stretch goals for my mathematical skills, right? Even Zed was getting real into the math today. Like, this shouldn't be so hard, right? Oh, we're gonna watch a little more of this.
Or point two. It's still...
Remember what we're doing here, okay? We want to have an in-depth knowledge of how, like, research methods work. We want to understand, like, if we read a scientific paper, in order that we are not fooled, we want to be able to understand what they're talking about. And a lot of that is going to be very dry. That's just the nature of the beast, right? It's the nature of this. Or maybe on the other hand, maybe you find this very entertaining. Maybe this is your idea of like a good like Saturday, Sunday night. Just sit back, relax, hang out with possibly the coolest person that exists in the world, yourself. But then also me, you know, I'm up there. And we sit around and we watch statistic videos. Maybe that's your idea of like the best time in the world. And if that is your idea of a good time, and you find this very enjoyable, please consider supporting me at patreon.com/mindofmeaning. I would greatly appreciate it. And with that, we're going to watch a little bit more of Zed's statistics. I realize I'm jumping around a lot. I need the novelty of different things to sort of start to converge to some kind of a sense make thing, product, a product of a sense make. You make something, the sense makes something. It makes sense to me. Anyway, let's go.
Possible for this null hypothesis to be true, yet our sample just be very extreme. So essentially, we create artificially, mind you, this region beyond which we're, sure enough. And so this yellow area represents the chance we're willing to take on board that we're actually going to be incorrectly rejecting a true null hypothesis.
Okay.
Now, why 0.05?
Yeah, why?
Well, they won't tell you this in your lecture, but there's no reason at all.
Oh, that's
Statisticians
good to know.
love
It's convention.
0.05, and of course, we're attracted to it because it's nice and round. But it's completely arbitrary. Someone chose 0.05 many years ago, someone probably by the name of Fisher or Box or something like that, and all of a sudden it kind of stuck, and most statistical tests these days are done to the level of significance of 5%, and that's what alpha represents there. So it's essentially the probability of us being wrong in rejecting the null hypothesis, and that's termed a type 1 error. We'll be looking at type 1 and type 2 errors a little bit later on in this video as well, but
we're going to just... This seems important to
tests these days are done to the level of significance of 5%, and that's what alpha represents there. So it's essentially the probability of us being wrong in rejecting the null hypothesis, and that's termed a type 1 error. We'll be looking at type 1 and type 2 errors a little bit later on in this video as well, but that's what it means. So what's going to happen is we can calculate this critical value, this point beyond which we'll be rejecting the null hypothesis.
Okay. We can calculate the point after which we would reject the null hypothesis.
Then calculating our test statistic to see where, or in other words, in which side of this critical value our test statistic lies. So let's do it. Let's go to test statistics. So as I said, our sample difference is distributed normally with a mean of 0, and this is our variance, p, 1 minus p times 1 on n1 plus 1 on n0. Now, if that's the case, let's consider this test statistic that we're going to call t, where it's going to be the sample difference divided by the standard error of that sample difference. So it's essentially theta hat divided by the square root of the variance. Now, if theta hat itself is distributed normally with a mean of 0 and a variance of all this junk, then t, our test statistic, will be distributed normally with a mean of 0 and a variance of 1. It's quite simple to prove there. If you take the variance of this expression, it's just going to be the variance of theta hat, which is this, divided by that squared, which is in fact that again. So it'll cancel out and you'll get 0 and 1. And the good thing about doing that is that we've now created a very standardized test statistic, which we can compare to things like normal distribution tables and things like that. Another way of thinking about it is that the test statistic is just a scaled version of the sample difference. It's just scaled by a factor of the standard deviation. We've just divided.
Okay, so what I'm understanding this here, this test statistic, appears to be doing the thing with that, the axiom, the second axiom of probability, the normalization axiom, right? So that's cool, because we're in statistics now. This isn't probability, this is hypothesis testing, which probability plays a part in, but we're actually in the context of statistics. Anyway. if you joined me today, I want to greatly express my appreciation for your joining of me. And I'm probably gonna take a step away for the moment. But if you've enjoyed any of this content, thank you. If you've enjoyed it, consider supporting me on patreon.com/mindofmeaning. This channel is about the truth and ways in which we find the truth. Now, right now, we are currently on a journey to understand probability and statistics so that we can understand science, because science is a very important epistemic tool for understanding the truth. So, we are learning how to understand science better. One, so we can not be fooled. Two, so that we can just be more connected to reality. So probability and statistics is our first step on that particular journey. But we will also be pursuing other things on this channel too, other ways of understanding the truth. I'll come up with some examples at some point of other things I'm thinking about. I'm just sort of trying to get my mind around how I want this channel to be like. So thank you if you've joined me. I greatly, greatly appreciate your time, your attention, and I will see you next time. I have to put a halt to this right now because I gotta go eat some food and probably go do something else. But thanks for joining me, and I will see you next time. Peace.